The Fourier transform is a very powerful tool to analyze LTIC systems. We know that the output of an LTIC system, which we will denote y of t, is the convolution of the impulse response of the system, h, and the input signal, x. Applying the Fourier transform shows us that the Fourier transform of the output signal is equal to the Fourier transform of the impulse response multiplied with the Fourier transform of the input signal, x of omega. H of omega is equal to y of omega divided by x of omega, and we call it the frequency response of the system. Since the frequency response h of omega is the Fourier transform of the impulse response, it is given by the integral between minus infinity till infinity of the impulse response h of t times e to the minus j omega t dt. One major advantage of analyzing LTIC systems in the frequency domain is that we have to multiply h and x to get the output y instead of the convolution in the time domain. Let's consider the following example. Our frequency response h of omega is given by a rectangular function of omega with width 10, so that the frequency response is 0 for all frequencies up until minus 5 radians per second, 1 for all frequencies between minus 5 and plus 5 radians per second, and then 0 again for all frequencies greater than 5. Let's assume our input signal x of t is the sum of two cosines. The first cosine has frequency 3 radians per second, and the second cosine has a frequency of 8 radians per second. In the frequency response, this is represented by two direct deltas for the low frequency component at plus and minus 3 radians per second with height pi, and two direct deltas for the higher frequency component at 8 radians per second and minus 8 radians per second with height 2 pi. Now multiplying both signals in the frequency domain yields the signal y of omega. Since x of omega is 0 for almost all frequencies, y of omega is also going to be 0 for almost all frequencies. We only have to look specifically at the frequencies plus and minus 8 radians per second and plus and minus 3 radians per second. The frequency components of x of omega at 8 and minus 8 radians per second are multiplied with the values of h of omega at omega equals plus and minus 8 radians per second, which are 0, so that y of omega is also 0 at 8 and minus 8 radians per second. However, the two direct deltas at plus and minus 3 radians per second with height pi are both multiplied with value 1 of h of omega for those frequencies, so that the two direct deltas remain a part of y of omega. Hence we see that y of omega is equal to pi times the direct delta of omega minus 3 plus pi times the direct delta of omega plus 3, which shows that y of t in the time domain is equal to cosine of 3t. This verifies that h is indeed a low-pass filter, because the high-frequency component with frequency 8 radians per second is filtered out, and the low-frequency component with frequency 3 radians per second is passed through the filter. This ideal low-pass filter has cutoff frequency 5 radians per second. Determining the output of an LTIC system if the input signal is a simple sine or cosine is very simple, but we can use the same trick to determine the output of all LTIC systems to all input signals. For this, let's go back to the equation y of omega is equal to h of omega times x of omega. Keep in mind that h and x are complex numbers, so that we can express them in polar form by the magnitude times e to the power of j times the phase, which we can do for h of omega, but also for x of omega, and the output y of omega. Writing all signals in polar form yields, hence, the magnitude of y must be equal to the magnitude of h times the magnitude of x. And the phase of y has to be equal to the phase of h plus the phase of x. Applying the logarithm to the magnitude equation allows us to write the logarithm of the output signal y as a sum of the logarithm of the magnitude of h and the logarithm of the magnitude of the input signal. Remember that in order to calculate the output signal y in the time domain, we would have to solve a cumbersome convolution integral. In contrast, in the frequency domain, the phase of the output signal y is given by a simple sum, and when using logarithmic scale, also the magnitude of the output is given by a simple sum. Bode simplified this analysis even further by developing a standardized way to draw the frequency response of signals and systems. In his honor, we call those illustrations Bode plots.